Spencer, this is a pretty good mini version of what your test is going to look like. Okay. You need to know your right-hand rules. There are 3 of them. You'll need to know the force on a moving charge, the force on a wire, and the size of the magnetic field created by a solenoid. So here we go. Number 1, a conducting wire is carrying current towards the top of the page as shown below. Due to the presence of an external magnetic field, the wire is experiencing a force out of the page. So if I wanted to draw this, I would say the force is out of the page. How am I going to figure this out? Current up the page. This is the 3rd right-hand rule because there's an external magnetic field and a force. So I point my thumb straight up. I want the force to be out of the page. The force is my palm. So I'm going to point my palm like this. Stop curling your fingers. Stop doing this. You've just introduced a 90-degree bend and everything you're doing is wrong now. Okay? I got to bark on people for that. Can't be doing that. It's high-five, thumb out like you're going to shake someone's hand. Okay? Not like this. Like this. Not hitchhiking. For the force to be out, which way are my fingers pointing? A. Right, Kev? Up. Force. The force is from the palm, which way the palm points. So the only way my palm can point out of the page and the current point up the page is if my fingers point to the left. Suppose the magnetic field is changed and now the wire experiences a force pushing it to the left. So I'm going to use the same dealio, thumb up the page, but now my palm points to the left. Which way is the magnetic field pointing? Into the page. A stream of protons is acted upon by a magnetic force while traveling perpendicular. What speed? So protons is individual charges, so I'm going to use the magnetic force on an individual charge. I'm going to get the V by itself. The force is 5.8 times 10 to the negative 14. Q, it's a proton. Yep. And 0.6. This proton is traveling at I get 6.04 times 10 to the 5. If you got that right, 2 out of 2. Otherwise, I would probably do something like this. I would give you 1 mark if I saw that, half mark for the numbers, and a half mark for the answer. Next page over, number 4. A wire carrying a current of 5.2 amps is shown in the above diagram. If the force that the wire experiences, okay, what is the strength of the magnetic field? So now we're talking about the force on a wire, and that is given by Bill. Magnetic field strength is B, so that's going to be F divided by IL. So it's going to be 2.4 times 10, you know what? It's easier just to write 0.024, that's less typing, divided by 5.2. Which L am I going to use? The length of wire that's affected by the magnetic field. The 4.2, except I'll have to make that meters. 0.042. You get 0.11 units for magnetic field. Teslas. 2 marks if you got that. Again, otherwise I would give you 1 mark for that. You stop talking, please? Thank you. Half mark for that. Half mark for the answer. If you used the other length, if you used the 8 centimeters, I would give you 1.5. for 0.0577 Teslas. Okay. Oh, what's the direction of magnetic force? Current to the right, magnetic field into the page. Down the page. Now, what other two magnetic field rules, right-hand rules were there? There was for a single wire, you pointed your thumb in the direction of the current and your fingers curled in the direction of the magnetic field. That maneuver is when you actually curl your fingers. That's the first one. And then there was the solenoid rule. When you pretended to hold the solenoid in your hand, you curled your fingers in the direction of the current and your thumb pointed north. I can't remember if I put one of those on here or not, but there will definitely be those on your test. An electron traveling moves perpendicular. What's the magnitude of the magnetic force? Okay. It's an electron. B 0.0085 or 8.5 times 10 to the negative 3. 1.6 times 10 to the negative 19 times 6.2 times 10 to the 6th times.
It came up as negative 9.
Thank you. Times 0.0085. You get 8.43 times 10 to negative 15. Is that correct? Newtons. 2 out of 2 for that. Otherwise here, I guess I'd go 1 mark, half mark, half mark. You okay, Lyndon? Yeah, good, shut up. Oh, it's forced into a circle. Magnetic force is what's pushing me in a circle. QVB is equal to mv squared over r. One of the v's is going to cancel. They want the radius. The radius is going to be mv over qb, not qb over mv, because if you get the divide by mv, you've got 1 over r by itself. Mass, it's an electron, 9.11 times 10 to the negative 31. V, 6.2 times 10 to the 6th. Q, it's an electron. B, 0.0085. Let's see what we get. 9.11 times 10 to the negative 31 times 6.2 times 10 to the 6th divided by 1.6 times 10 to the negative 19 times 0.0085. You get 4.15 times 10 to negative 3? I need to change these numbers. That's a really small radius. Yeah?
Instead I just did FB equals MAC, and I got those same answers by putting the force in the bottom.
You did FB equals MAC.
Yeah, and then I did.
You still had to go MV squared over R somewhere along the way, though, right?
I did.
Yeah. Oh, okay. Yeah. You know what? I just, as a habit, if I don't need to use a previous answer to find the next one, just in case I made the previous one wrong, I probably even didn't even think about subconsciously as a habit, as a good test writer. I always got into that habit, right? So 4.15 times 10 to negative 3. Otherwise, I would probably do something like this. I would give you 1 mark if I saw that, half mark for the numbers, half mark for the answer. Oh, what's the kinetic energy? Okay. Ke equals a half mv squared. This might be nice if I gave you the radius and asked you to find v. I have no idea what. Sorry? You said lunch. Is that what you said? Quick like a bunny. Plan a little better. A half 9.11 times 10 to the negative 31. V, this is straight plug and chug, 6.2 times 10 to the 6th squared. You get 1.75 times 10 to the negative 17 joules. One mark, half mark, half mark. Solenoids. What's the magnetic field strength inside a solenoid of length 3.2 centimeters, having 600 turns of wire with a current of 4.5 amps? So, what's the variable for magnetic field strength? B. Most common mistake I see on questions like this is kids do this, and they go, oh, it's going to be Bill. They make up some nonsense for that, or they put the 600 there because they're desperate. They put the current there and they lengthen. They somehow think, oh, I found the field because field begins with F.
No.
What does F stand for in physics? Which is not a field. So B from a solenoid is mu naught N times I over L. Is that correct? I'm going from memory, but I think that's right.
Yeah.
And mu naught, the permeability of free space, what a great name for a constant, is 4 pi times 10 to the negative 7. This is where we said some of you may have found that you had to type pi 4 instead of 4 pi. 600, 4.5 divided by 0.032. 4 pi times 10 to the negative 7 times 600 times 4.5 divided by 0.032. Do you get a magnetic field of 0.106 Teslas? What if I wanted twice the magnetic field? Kieran, you're off your phone, right? Of course you are. What if I wanted twice the magnetic field? What could I do? Either half the length, or what if I have a standard solenoid base, twice as many wraps? You can, or build a circuit so it's getting 9 amps instead of 4.5 amps. What it really means is with a solenoid, we can customize a magnetic field however big you need it for whatever application you're looking at. And we can do it 3 different ways. We got a lot of options. It actually works really well. Those of you that are in mechanics, you'll know that car ignition systems have a solenoid. Right? That's sending out a magnetic field. That's sending out, I think, an oscillating magnetic field, and that's using something called induction, which we're not going to get to this year, which I hope to get to, but didn't quite. So, 0.106 Teslas? 1.06 times 10 to the negative 1. 2 marks. A bar magnet is free to rotate while in a magnetic field. It's initially positioned as shown. Which diagram shows the final orientation of the bar magnet? Pretty sure no.
Yes.
Okay. A or C? Magnetic field lines always point from what to what? So that means there's a north pole there and a south pole there. This south pole would be attracted there. This north pole would be attracted there. It's definitely A. That's also which way a compass would point. A compass points in the direction of magnetic fields. A compass points south because the end of a compass has a north magnetic pole on it. Can you give yourself a lovely score out of 16, please?